Until now, we've been working in electrostatics, and what that means is we don't have continuous long-term flows of charge. We might transfer it from place to place, but if we drop charge on a conductor, for example, it'll rearrange itself on the conductor's surface in well under a microsecond, and after that it doesn't move. Now we're going to start to look at charges moving over longer time scales or indefinitely long. We need the idea of a current, which is just dq dt, the change in charge at a given point as a function of time. It's the number of coulombs of charge per second moving past a point or through a wire, through a resistor, into a capacitor. We typically use I as the symbol of current, and 1 coulomb per second is also known as an ampere. Most of the time you call it an amp, and this is a capital A because, again, this is someone's name. Current suggests we're talking about something like water, and that's a pretty good analogy. If we look at a simple circuit like a battery connected to a light bulb, the current flows around the circuit, and it's the same everywhere as long as the wire doesn't split into two paths. This is the same way water systems work. It's the way escalators work. If we have 20 people per minute getting on the escalator, we have to have 20 people per minute going past the midpoint and 20 people per minute exiting the escalator. There are no other places for them to get on or off, and people are hopefully conserved. Now, if we want to think about explaining electrical conductivity, we have to think about the atomic level. Here, voltage difference between 2 points in a material makes electrons want to move. It would be easy to find the acceleration the electron feels, since we know acceleration is F over m and F is QE. The electron's mass is so tiny, even a very weak field will give it a crazy large acceleration. 1 Newton per coulomb, which is very weak, gives us an acceleration equal to 175 billion meters per second squared, which is huge. This might have you think that the electrons are moving through the wires, approaching the speed of light if they're under this ridiculous acceleration. The fact is, if we turn on a switch for a circuit and measure the speed that the potential difference appears across the light at the center of the room, we'll get speeds that are a significant fraction of the speed of light, usually around 75% or so. The electrons, though, aren't moving nearly that fast. The signal does, but the electrons don't. They're constantly bouncing off of impurities in the metal and dislocations in the crystal lattice, the what we expect to be regular Lego-like structure of the copper wire. There are dislocations where two different crystal domains meet. There are other electrons. There's all sorts of things that can slam into these traveling electrons and knock them backwards. This is kind of like this game you may have seen. I think it's on The Price is Right. You drop these discs down through these pegs, and I think you're trying to find out where they're going to land. But the big idea for us is, if you were just dropping the discs straight down a flat board like this, they'd take less than a second. But with all these pegs in the way, they keep bouncing back and forth. They bounce up. This makes the trip much, much longer, and it makes their effective velocity much, much slower. The actual speed of the charge carriers in the wire is known as the drift velocity, and it's much slower than the signal velocity, which is what turns the light on. There are similar effects if we look at if someone is unscrewing the cap on a bottle of ammonia in a big room. You'll hear the sound of the cap within milliseconds. The sound travels about a foot in a millisecond, but it will take several seconds or more before you smell the ammonia, before the actual particles get to you. If you have a garden hose out in your yard, as soon as you turn on the faucet, you may get water coming out of the end almost immediately, because the signal to get out of the way travels through the water at the speed of sound in water. On the other hand, if the hose has been sitting out in the yard in the sun, you notice that the first water you get out is very hot, and it'll take several seconds for the cold water to get from the faucet to the hose. You would get this same delay if you started with an empty hose, because you're again waiting on the actual water to get there. You can think of wires as hoses that are always full of electrons. Now, we can find this drift velocity if we know a few other things. We need to know the density of free charges. This is generally between 1 and 4 per atom in a conductor, and for copper it's 1 per cubic meter. This is 1 per atom per cubic meter. The charge on each carrier is just the electron's charge, the total current, and the cross-sectional area of the conductor. So the drift velocity is I over NQA. It's common to talk about current density rather than current, and current density would be dI over dA, the integral of J dA. So if we integrate this current density idea over the cross-sectional area of the wire, we'll get the current back. J is measured in amps per square meter, and later we'll look at cases where J is not constant, where perhaps it's larger at the surface than it is in the center, or maybe the other way around. The dot product here in this integral tells us that what's important is the current density that is perpendicular to the cross-sectional area, so what's pointed downstream, in other words. So we might use J instead of I over A here. If we do that, that means we can write drift velocity is current density divided by NQ. As long as we're always using the same material, copper for example, N times Q is just a constant. So what's a typical value of drift velocity? Well, really in your household wiring, since it's alternating current, they're going back and forth, changing their direction 120 times a second. Let's ignore that and play like we have DC wiring in the house. So let's say you have a high current appliance like a hairdryer plugged into an outlet served by 14 gauge wire, that's code. That's what you'll probably find if you open up your walls. According to Wikipedia, that wire has an area of about 2 square millimeters, or about 2 times 10 to the negative 6 square meters. The current for the hairdryer is going to be about 15 amps. And in copper, this number density of electrons is 8.3 times 10 to the 28 per cubic meter. So now it's a math problem. We put all this in and we get 0.00054 meters per second. That's half a millimeter per second. What about in your car? This is a DC system. The battery cables are usually 4 gauge, meaning they have an area about 10 times what we just saw, 2.12 times 10 to the negative 5 square meters. The current used in starting a car, if you have a large engine and it's cold in the winter, so the oil is sludgy, this can take several hundred amps. So this will give us a larger current density and we should get a higher drift velocity. We put in 700 amps and the area of the 4 gauge battery cable. We get 0.0025 meters per second. So that means in 1 second the electron travels about the thickness of 2 dimes. According to Google, a garden snail moves 5 times faster than this. Now we can talk about resistivity. This is the inverse of conductivity. So insulators would have a high value of resistivity and a low value of conductivity, and conductors would be the other way around. The connection between the current density, the conductivity, and the E field is a very important one, and we write it as J equals sigma E. Sigma is the conductivity. Here we're treating it like a scalar. That's all we'll ever do with it, but in reality, just so you know, it's what's called a second rank tensor. Vector is a first rank, a scalar is a 0th rank. The idea is just as the vector E here in 3 dimensions has 3 components, this thing would really have 9 components. It would be a 3 by 3 matrix because real materials conduct better in some directions than others. We're not going to worry about this ever again, and we're going to assume that sigma just depends on what the material is and it's a scalar. This relationship is the real Ohm's law. Unfortunately, almost nobody means this when they talk about Ohm's law. We're going to see what they refer to as Ohm's law later. But this is a real law in that this is the way everything works. Now, what it tells us is a stronger E field will give you a larger current density for a given material, or for a given E field, a better conductor will give you a larger current density. Resistivity is probably used a little more commonly than conductivity, especially in intro physics, and the units for it are ohms times meters. Now there are special things called superconductors, we'll talk about a little bit later, that have 0 resistivity, but we would need liquid nitrogen temperatures to make this happen. If we stay at room temperature, our best conductor is silver, and it has a resistivity of 1.59 times 10 to the negative 8 ohm meters. Copper is about 3 times worse at 5.95 times 10 to the negative 8. Gold is in between at 4.1 times 10 to the negative 8. So gold is actually a better conductor than copper, but silver is a better conductor than gold. Why don't we put the silver as a conductor on our computer cards, things like SD cards and the video cards in your computer? Why are the connectors gold plated instead of silver or copper plated? Well, if you look here, you can see this is what happens to silver over time. It tarnishes, and copper becomes tarnished as well. It looks green. This is why the Statue of Liberty is made out of copper, but it looks green. Gold doesn't tarnish. Now, most metals in general have resistivities that aren't far off of these values. Semiconductors, what's used in a computer chip, there we can have resistivities from 10 to the negative 5 to 10 to the 4th ohm meters. Glass, 10 to the 9th to 10 to the 14th. Things like quartz and rubber, we could go 10 to the 16th to 10 to the 18th ohm meters. That's a range of 26 orders of magnitude, and I can't think of any physical property that has a range anything like that. That's why it's so ridiculous to take this huge range of possibilities and shrink it down to binary, yes or no, conductor or insulator. Now, resistivity does have some temperature dependence, and in general, it increases linearly and relatively slowly with temperature. We're going to ignore this because we've got enough to worry about, but also because the resistors that we have in the lab, and most of the ones that people use in general, the resistance doesn't change much over the temperature region where they're going to be used. If they did, they would be better as thermometers than resistors, and there are things like this out there. They're called thermistors. We are going to consider ρ to be a constant for a given material, so we're going to ignore temperature dependence. Now, just like the permittivity of material in a capacitor is not usually what we care about, we usually care about the capacitance, again, because we're not in the business of making these things. We usually care more about the resistance of the final object than the resistivity of the material inside it. So capacitance depends on permittivity in geometry, resistance depends on resistivity in geometry. We're going to assume our resistor is cylindrical because that's a very common form factor for them. And our formula is the resistance R is ρ times L over A. L is the length of the cylinder, A is its area. The units of resistance are ohms, and this is again somebody's name, and our symbol is the Greek capital Omega. The formula here is what we would need to know if we were going to go into business making resistors, just like we'd need to know C equals epsilon A over D if we want to go into business making capacitors. Now, what's the connection between the voltage across this resistance and the current through it? This we get from what practically everybody means when they talk about Ohm's law. This, if you ask the person on the street what's Ohm's law is, and they actually know, they will probably say V equals IR. What this means is if we put a potential difference of 1 volt across a 1 ohm resistor, we'll get a current of 1 amp. We buy resistors so that they obey this relationship. Here you can see a collection of common resistors. Again, these are the sizes we would use in the lab. The ones inside your phone are much, much smaller. The different physical sizes of the resistor, what they typically mean, larger physical size means it can dissipate more heat without damaging the resistor. Because resistors turn electrical energy into heat, and if you try and dissipate 10 watts of power through a quarter-watt resistor, this little thing here about the size of a grain of rice, it'll probably catch fire. Notice that they also have different colored bands on them. This is a code, and you can either memorize it or look it up, and it'll tell you what the resistance of each of these is. You can also just look with a multimeter, and that's kind of the lazy way, but it certainly works. When you're buying resistors, you have a bunch of options. You can choose resistance, maximum power. You can also pick from a variety of tolerances. Very commonly, you get 10% resistors, which means If you buy a 1,000 ohm resistor and you get anywhere from 900 to 1,100 ohms, you got what you paid for. 1% resistors, still about a penny a piece, so that's typically what we buy in the lab. There are a lot of different physical sizes. There are resistors with different temperature coefficients. If you look around our lab, most of what we have are 1% resistors with a power limit of 1/4 watt. Now, as the voltage across a resistor increases, the current through it increases linearly, and that's what obeying this Ohm's law, that's not really Ohm's law, means. Not everything obeys that. That's why it's not really a law. Things like LEDs, light-emitting diodes, or incandescent bulbs don't obey this. Diodes, whether they're LEDs or the non-light-emitting boring kind, are like a one-way street for current. They only allow current to go in one direction. It's very, very easy to go one way. And this value here, the current that is allowed to travel when you're on this negative side, when you're going the wrong way down the one-way street, this is actually a super tiny current until you make the voltage so large that you essentially break the diode. This side, which is where you would expect to use the diode, this is an exponential rise in current. This is why if you've ever done anything with electronics and used a diode, you have to have a resistor in the circuit or you will burn the diode up very quickly. Things that look like this are called non-ohmic devices. They don't obey that thing that people call Ohm's law. Now, the power that's dissipated in a resistor we can find from the work formula. We know W equals Q delta V, so we know power is dW dt, so we can write delta V dQ dt, or I delta V is our power. If we're looking at something that obeys this thing that even we will call Ohm's law, even though it's not a law, we can write the power dissipated as P equals I times V, or I squared R, since V equals IR, or V squared over R. The energy we use is P delta T. Now remember, Georgia Power doesn't bill you for power, they bill you for energy. The only thing that's weird is instead of using joules, which we would use for energy, they use kilowatt hours. So this is 1,000 watts for 1 hour. If you leave your microwave is probably about 1,000 watts. If you run it for an hour, you'll have used a kilowatt hour worth of electricity. This is 3.6 million joules, and this is in the ballpark of 10 to 15 cents, depending on time of year and things like that. Now, the last topic in this chapter is superconductivity, and up until about 1986, this was pretty much a dead area of physics, and you would see it in maybe a modern physics class, but that's it. They figured out in the early 20th century that at really super cold temperatures, like a few degrees above absolute zero, the resistance disappeared for a few materials. They could not find anything superconducting at temperatures above 18 Kelvin, and you need liquid helium to get down to temperatures that low, and it's super expensive. Now, in 1986, somebody found a material that was superconducting at 92 Kelvin. This is a little bit above the temperature of liquid nitrogen, which is much, much cheaper, so this was a very big deal. Currently, the record is somewhere between 135K and maybe 250K. I don't know if that's going to be confirmed or not. The big deal here is that if a room temperature superconductor could be found, that would be around 300K. We could get rid of the energy loss in electrical transmission lines, and according to the government, their estimates, somewhere around 200 billion kilowatt hours are lost just in moving from the power plant to the user in 2019. So this would be a really big deal. This would be a very fundamental change in our energy situation.